the sound from your laptop muted. All right, everyone, you're at the Measurement and Analysis for Protocols Research Group meeting. In a momentary lapse of reason, we invited 10 speakers to talk today in 2 hours' time. So there's on the, what's that? It's good to have goals, yeah. So this is going to be the good news is it's going to be a whirlwind thing. If you don't like what's going on now, wait 5 or 10 minutes and it'll be a completely different presentation. So that means we only have about 10 minutes to spare. So I'll apologize in advance if we're cutting you off, but it means that when you see the timer up there, most of the time to ask questions or contribute comments is during the timer being there. We'll tell you if we're out of time, but like I said, it's about 10 minutes to spare. So let's see, let's get through the boilerplate here. The IETF observes the same. Oh, I should say we should introduce ourselves. Getting ahead of myself. I'm Dave Plonka. I'm the co-chair of the Measurement Analysis for Protocols Research Group.
Hi, I'm Mia Kühlewind, and if somebody in the back could close the door, that would be nice.
And if we have newcomers, we are a measurement group that brings tools and measurement results about the operation and the design of internet protocols in the IETF. So we get to do quite a survey of different topics. I believe this is the 10th year of us meeting, possibly this meeting. So it's been going a long time. Thank you for being here. The slide that's up right now, the intellectual property, the IETF uses the same intellectual property agreement as the IETF. If what you're presenting today has intellectual property encumberments, then you need to tell us about that soon after the presentation if you haven't already. More boilerplate, the note well. Let's see, we're being recorded, of course, so if you're up at the mic or whatever, regardless of whether you have the red lanyard or not, you're acquiescing to that. And we have a privacy and code of conduct. Behave yourselves at least as well you have earlier in the week, please. And the goals of the IETF, we run a little more loosely than the IETF, but largely we're a research organization, not a standards development organization, but happen to be able to be co-located with the IETF. There's a slide here with where you can find our mailing list. If you aren't joined already, it's very low volume. If you think you want to present at a future MAPRG, it's a good place to be because most of the talk on it is about is our call for contributions. So that's how you get there. There's links to the other tools for this meeting here, but you probably found those already via the agenda. Keep your video and audio off when you're not presenting. Those of you that will be presenting, we're going to put up your slides and we'll pass slide control to you. So the agenda, I've got some timings just for my own sake in the agenda. I said 10 presentations. We kind of do 3 kinds of presentations here. Full presentations about either published work or quite mature work, where you get, in this case today, 10 or 15 minutes. We're going to do a couple of heads up talks to let the community know about what kinds of things are going on. That there's short talks just because that's the only amount of time we had in the meeting today, but it's to let you know, or it's to help us measure or engage interest in the group and those things. And then lastly, the other kind of presentation we do, which is similar to the heads up, is if you want to offer us a slide, we'll show it in front of everyone. So we have one of those here. I won't go through the agenda in detail because you see them as they're coming up, but Tom Vaughn from Common Crawl has done a nice piece of work about IPv6 adoption, showing us a small uptick in adoption over the last couple months. There's a QR code here, and you can also find the URL to the full report for that in the chair's slides, the first slide presentation.
Yeah. Tom, are you here? Can you raise your hand so people can talk to you? But I'm not seeing him. He might be late. Okay.
All right. So on time thus far. First up, we have Johanna Rooney, and I'll bring up your slides, Johanna, and we'll pass control to you.
Thank you.
What?
How do I stop this one?
In the corner here.
There we go. And then the slide control. All right, Joanna, I pass the slide control to you, and I'll start a timer as soon as I find the button to do that. We got,
But you can start.
Okay, give me 1 second, sorry.
We can hear you.
Okay, so hi, I'm Joanna Moran. We'll be doing our talk today, which is towards a common measurement framework for large-scale LibTP deployments using CBOR-based verifiable telemetry. So the networking layer of large peer-to-peer networking deployments has matured, but our measurement infrastructure hasn't kept pace. Every ecosystem observes the network differently, which makes results hard to compare or verify. And so we're proposing a common measurement architecture built on portable cryptographically verifiable telemetry. So slide 2. So here's the paradox. Many decentralized ecosystems already share the same networking substrate, LibTP, but every project builds its own observability stack, which its own metric, logging formats, and semantics. The result is fragmented, so the two deployments can observe the exact same protocol event and describe it completely differently, with its own metrics, logging formats, and semantics. So the result. So today's observability tools are. 1 second there. Today's observability tools are built for operators. Dashboards, logs, and traces are great for real-time debugging, but they're poor scientific artifacts. Dashboards disappear, log formats change, schemas evolve. What we actually need are portable observations that stay meaningful long after they are first collected. So I'm just going to go. So this is our proposed architecture. At the bottom sits independent libTP implementations and applications, each generating observations locally. Those observations get normalized using common measurement vocabulary, then encoded into standardized telemetry objects before being shared with researchers, operators, and AI systems. The key point, implementations stay independent, only the measurement representation becomes standardized. So this is the core contribution of the framework, the verifiable telemetry object, or VTO, and each VTO packages our observation together with standardized metadata, timestamps, provenance information, cryptographic identifiers, and integrity protection. So instead of deducting whoever produced the measurement, anyone can independently verify that it hasn't been altered. The telemetry object becomes a portable unit of scientific evidence. To make these artifacts portable, we need deterministic encoding so that we use canonical CBOR. Identical observations always produce identical serialized representations, which gives us stable hashes, digital signatures, and content addressing. Compared to JSON, CBOR is also smaller and more efficient to process. So insert the Internet of Agents. Okay. This matter, sorry, 1 sec, oopsie. So this matters even more for autonomous agent systems. Modern agent infrastructure involves thousands of independently deciding software agents. The traditional logging isn't enough. Portable telemetry gives us a common evidence layer for debugging, accountability, and coordination across heterogeneous agent ecosystems. So our conclusion here is, let me go to the slide. Our central argument is simple. Measurement interoperability should evolve alongside protocol interoperability. If decentralized systems are to be scientifically reproducible, comparable, and trustworthy, we need standardized measurement artifacts, not just standardized protocols. By combining common measurement schemas with CBOR-based verifiable telemetry objects, we believe we can establish a portable evidence layer for the next generation of decentralized and autonomous networks. Thanks so much for everyone. Happy to take any questions. Appreciate the 5 minutes we got today. Thanks a million.
Yeah, thank you, Johanna. So you were initially looking for a longer presentation, but we had a lot of requests this time. But we wanted to give you the opportunity to present this work if anybody's interested, so they can reach out to you and work with you on this, and then maybe you can come back later in time with more results.
Yeah, thank you so much. I really appreciate it.
And Johanna and Manu, please put your contact information in the public chat if you want, or let us know how you want people to reach you.
Sure, just did that. Thank you so much, Dave. Really appreciate it. Yeah.
Thank you. Paul, you can come up.
Hi, everyone. I'm Paul Carlton. I work at Anthropic.
Hold on a sec.
I'll just give you my intro while we're short on time. So I'm one of the core maintainers of MCP, and I'm going to be talking about MCP's profile of OAuth 2.1. So for some background, MCP wants to support clients and servers in OAuth that have not seen each other before, being able to connect to each other. So what that means is to avoid the pre-registration step that is typically in a normal OAuth deployment. The way we recommended to do that in March of 2025 was with dynamic client registration, which looks something like that. I don't have time to explain the whole diagram. One of the issues we had with this recommendation was around client IDs becoming stale and being purged in the authorization server. So you would try to authenticate and or try to authorize, and you would get back an invalid client grant and then have to re-go through the registration step. So in November of 2025, we started recommending client ID metadata documents instead of dynamic client registration. So this, instead of doing a registration step, you provide a URL as your client ID, and the authorization server goes and looks up the data there. So I've got some data for how that's going at Anthropic for our client. So this is the adoption growth we see of client ID metadata documents. This is for connector authorizations. So in the last 30 days, we saw about 14.7% of these sign-ins using client ID metadata documents, which is great to see. And then, well, I guess it's only great to see if it actually solves the problem that we were seeing. And the nice thing is we do see a lot fewer of these requests hitting the invalid client requests. So we see DCR hits this on about 0.2% of refresh attempts, where static client IDs also hit it at a lower rate, and then CIMD is 0.002%. So it's about 100 times less than you see with DCR. Yeah, that's what I've got. Thanks.
Perfect, thank you. You are also coming big with more data next time, I guess. Any quick questions? Otherwise, Paul is here. Talk to him.
All right, so next we have up Dan Silva, and this is in a way a different methodology, but it's a follow-up to what we did a year ago when we had a session specially dedicated to crawler traffic. And let me get your slides up here, Dan, and pass the control to you, and you'll have 10 minutes. And thanks to Paul, we'll have some time for questions and comments too.
Great, thanks, Dave. Yeah, as Dave mentioned, I have. He said it's been about a year, and there's been an upswing in bot traffic. So this is kind of a exploration of that a bit. There's a couple interesting projects that this was kind of inspired by. Nepenthes is a traditional slow tar pit for bots to kind of get stuck in and move slow. And then there's other flavors of bot traps, like the Library of Babel is essentially every single book and whatever that would ever be written. So every character and combination of that. And then if you kind of go on to the more scientific scholarly articles, there's a couple tools out there that have fake information and that kind of thing to kind of poison the well. So the idea is, like, what happens if you publish a valid robots text file and then you have theoretically an infinite amount of content and you don't manage the traffic at all, or block or throttle the bots? So that's kind of the approach we took. And this is the site that we came up with. It's the American Corporation for Public Wellbeing. It's not a real company. It attempts to be authentic and authoritative, and it's very text heavy, easily crawled. There's a simple structure to it. It's got all kinds of fake business things. It kind of represents this like think tank business. So we kind of went towards more quantity than quality. So we're not trying to poison the well. We're kind of just seeing how much content we can serve, how fast we can do it. Some of the AI models have been able to sniff this out, where there's something, they detect something's wrong, but they don't really explain why it's how it is. So here's the results. We spun this up about 5 months ago in mid-March. And as you can see, these bots just don't seem to want to leave it alone. In July so far, we're averaging about 5,000 requests per minute. We just crossed about 1 billion requests served in those 5 months. The top 5 bots represent 75% or greater than 75% of requests. Most of those URLs in the 1 billion are unique. And with the way the site's structured, that's kind of on purpose. About 2 million hits on robots text. So most bots are checking that, most are following it. And peak traffic has been about 1,500 requests per second. And before gzip compression, that's about 1.5 gigabits per second. I did not expect to have to build up a small cluster for a site to serve basically what is garbage to bots, but here we are. Here's a kind of a breakdown of some interesting bad crawler behaviors. Most of the bots are not completely out of control, but one in particular is far more aggressive than others, and that's Quen, which is an Alibaba cloud project. It's extremely bursty. We've seen sudden peaks of over 1,000 requests per second for 1 minute or less, and then nothing at all. It also is not truthful about its user agent. It sends a basic web browser user agent, and it always sends a Google HTTP refer. Some bots also ignore HTTP redirects. So if you're trying to change paths or move things around in the site, they just don't follow that. And an additional note about the Quen bot is if your site goes down for an extended period of time or even a little bit, it does not do any kind of exponential back off. So it will come back and possibly with even more traffic. So recovering from an outage is interesting after Quen causes one. Here's kind of a quick breakdown of some of the numbers. If we got about 1 billion requests, Quen is about a quarter of them, about 30, it's probably higher than that. I think it's more like 30%. And then that's followed by OpenAI and Tencent and Claude. Here's kind of a layout of the app. It's just a very simple web app. Traffic ingresses into a basic Nginx load balancer, which then fans out to a cluster of Django workers that generate the content pretty much. And then stats flow into Redis, which is processed later. That's all async. So it's really a very simple setup. One discovery that we've had is subdomains seem to amplify traffic for some bots. Some of the content is actually segmented into separate subdomains. So the theory here is that the subdomains are treated as a separate website for some of these bots. And when you're routing traffic in them, they obviously are rate limiting that differently somehow. And there was definitely a jump when we enabled the subdomains of some of the bots doing something different, which was kind of interesting. There's a bunch of different pieces for the site, and I don't have a lot of time, but the one that gets the most attention from these AI bots is what we call the archive, and there's about 600 million requests served for that. The archive kind of works in a way that the URL actually seeds it picks, there's a library of pre-generated content, and the seed from the URL, which is made up of a bunch of different pieces, actually selects random stuff from the library, and that that seed is consistent over every page view for that one specific URL. So it's, if you go back to the same page, it's the same content. So that's kind of how most of the site works, and it's all just pre-generated random text that's kind of glued together. It's very fast. It's about 10 milliseconds per page load. So Cloudflare has their lava lamp experiment for generating entropy. We kind of built a similar thing where we're using AI bot traffic to generate random numbers. So there's a separate spin-off site that gets live requests from ACPWB. And the concept here is we're using the bots as a source of entropy. Not sure it's totally kosher and for random, numbers or whatever. Probably wouldn't use it for that, but that's what we got. Future experiments, we're currently kind of implementing internationalization just to see if that changes things, if the bots that are not primarily English or expecting English do anything different or are more aggressive or interested in things. But that's what I got. I'd like to thank Anton Capella. He donated compute and network resources for this project, and just let me know if you have any questions.
Thanks a lot. I can say the talk was well appreciated in the room.
Thanks.
Laughter at all the right places. So go ahead, Stuart.
I'll be really quick because I know we're down by time. I'm Stuart here from my
Our time is pretty good.
And I actually came up to say exactly that thing. I wish you were in the room because people are almost falling off their chairs laughing here. This is spectacular. It's fantastic. Thank you.
Great. Thank you.
Dan, maybe I missed it. I was curious to know what challenges you had, if any, with identifying what the company or the bot was, because I think I heard you say that they lie about who they are. What are we presented with there?
So you can look up the network that they're on, and sometimes that tells you. I know some of the Alibaba cloud stuff actually goes, you do who is for that, and it tells you exactly who it is. But they also seem to be getting new subnets in other places that are not as easy to look up. So you can kind of identify it by obviously they're always sending Google as the refer, like every single time, same thing for every request. So that's a pretty good tell.
That's pretty interesting. So it's kind of a fingerprinting exercise, really.
Yeah.
And then you mentioned you were able to look up the ASN there. Two anecdotes. At my small research and education network, we've had to block traffic from outside the U.S. temporarily while we're trying to figure out how to deal with the deluge of requests to our public sites. And so that's an anecdote of what's happening to some people. The other one I know about, a geology department at the university, they were seeing these kind of requests from tons of what looked like residences. So have you seen anything like that where clearly they're trying to hide it as normal users?
It seems to be most of them come from a pretty the same IPs. Like there's a couple IPs that are, for Quinn, it's always the same blocks. They kind of rotate occasionally, but it's not residential at all.
All right, thank you. We got a couple more people in the queue. Robert, you're up.
Yeah, thanks. Robert Story, USC ISI. I see you have a GitHub repo here. Is this open source? Like if we wanted to reproduce it?
I can put it back up. I took it down because I wasn't sure if the bots were going to start sniffing that out, but I can put it back up.
And my second question was, you talked about introducing languages as a way to maybe see if it would slow them down. Have you tried other things to see if they notice, like if you're rate limiting or other things like that, or you're just keeping it wide open?
It's wide open.
Okay, thanks.
Thanks. And next in the queue, we have Tim.
Sorry, hi, Tim Chan. Yes, yeah, this is great. Thanks. I'm a bit naive in this area. Just how much more aggressive and out of control are the AI bots than the normal crawlers? Presumably, you still want to have your wonderful website appear in Google and Bing or whatever they're called, and you wouldn't want to block that. That's useful, but just what's the relative craziness?
That's a good question. I mean, I went back to the slide with the stats here, and you can see Google's at the bottom, and there I think it was about 5 million requests from them out of a billion. So it's a pretty small percentage. The legitimate search engines that are, the traditional search engines, they're a drop in the bucket for this.
But does number
And
4 suggest that 12% of the hits are people reading your site and maybe believing it's true? The browser.
so that's something I haven't totally explored, and that is part of the problem with Quen is I have to, in the software, actually tell it subnets that Quen is on, and a good chunk of the other browser one isn't. That's not totally accurate because that's just unclassified, and I need to do more work in this. But yeah, I mean, the traditional traffic from search engines hasn't really been significant.
Okay, great. Thank you. Really good.
Thank you.
Out of curiosity, did you also try different top-level domains like .net, .com, and then maybe country-specific ones?
Not yet. We haven't done that. I have a few more, the $10 domains laying around for abandoned projects that I probably should try, but no, I have not.
Okay, yeah, thanks.
Yep.
All right. Thanks a lot for joining us, Dan. I appreciate it.
Thank you.
Oscar and Max, I think we have you up next.
Yeah, thanks. Hi. Grab this. Yeah, that's fine.
Almost there.
So yeah, hi, Oscar and Max from the Firefox networking team. And yeah, we're kind of just here to share some data with you today. We'll try to be brief. And now this works, great. Yeah, so basically, yeah, this just says, yeah, we do collect telemetry data and it might be relevant for the IETF. I think the last point is the most important one. The low resolution of this is entirely public, and you can sort of just look at all the probes in a low resolution aggregate. And that's also what we kind of want to motivate people to do. So yeah, this can easily be looked at. Let's get into it. So we kind of just prepared a few fun things that we thought surprised us, might surprise some of you. The first one is just OS share. And so yeah, a lot of our traffic is Windows. What might surprise you is about a third is still Windows 10. And then we have 6% that are even older than Windows 10. And in general, we also have like a very long tail of machines that are slow and old. And I think that's something that we as devs maybe often forget, that not every machine out there is a dev laptop. So yeah, for example, you can see here we have 11% on 4 GB of RAM, and we have 7% still running 32-bit. Then for mobile, so on Android, we see a split of 60% are on Wi-Fi, and then about 30% are on mobile. Which might be interesting for some of you. And then at this point, I'll give the mic to Max.
Okay, so I'll walk up the stack a little bit. All of these metrics are rather fun facts to like keen your interest. You can dive into each of these, and you can download the slides, and you'll find the links to all the different metrics. Explore some more, and Oscar will go into detail how you can find all of them. So if we walk up on the IP layer, right now Firefox still sees very little IPv6. 20% of our requests are over v6. The remainder is over v4. This is with Happy Eyeball v1, which are our current release numbers. We are currently implementing Happy Eyeball v3. That's in Firefox Nightly, which is our alpha version. But there we don't really see a big change in this number. If we walk further up, contrary to IPv6 adoption, HBS is pretty much universal, or we consider it pretty much universal. 89% of our requests are encrypted. The remainder is basically half and half, either plain text or requests to local domains, where we're not so worried about this not being fully encrypted. I assume a lot of the unencrypted part is enterprise setups, but there I cannot validate that from the outside. If we walk further, we we use HTTPS to encrypt the actual good put. What is relevant for us is to encrypt the SNI, the server name indicator. You can do that with the ECH, encrypted client hello. That is, we see very, very low deployment of ECH. Definitely below 1%, around 1% sometimes. We see more ECH deployment on HTTP3, but I think that's simply a correlation, not a causation, where those hosts, which is basically just Cloudflare free customer offering, we mostly connect to them via HTTP3, and thus we see more ECH on HTTP3. Talking about HTTP versions, HTTP3 is around 17%. We mentioned this in various other venues here. The majority of our requests are still HTTP2. All of these numbers are page loads and not actual number of requests. Why I chose this metric here is if you, for example, go to any major news site, you'll make one connection to the news site and then 100 connections to various ad trackers. So I'm excluding them here by simply measuring page loads. There are other perspectives on the number of HTTP3. So for example, Cloudflare Radar reports roughly 30%. And for those interested, there was the More Quick How site meeting with a lot more information on this. Now, discovering HTTP3 is a little bit difficult. You might remember when we upgraded from HTTP1 to HTTP2, which I guess we're still doing. The upgrade would happen on the TCP connection via APN in the TLS handshake, so you can reuse the TCP connection. That doesn't exist in HTTP3 as that is using QUIC, so there's no shared TCP connection. So we need some signal from the website operator that they speak HTTP3, and there are two ways for that, either via an L service or an HTTPS RR DNS record. The former, we would first have to connect via H1 or H2, and we see actually that happening in most of the cases. Around 35% of our upgrades use L service. And then via HTTPS records, we can connect via H3 on the very first connection, which is wonderful for us as we do way more HTTP3 as a browser. But that only happens in very rare cases. In addition, we shipped Quick v2 recently. We see roughly 0% deployment of Quick v2 on the internet. There are some caveats to this, and we discussed this in the Quick working group. So find me if you're interested in learning more about Quick v2 and maybe how we can progress that long term. A gotcha for me, just to interest all of you. So we run our own quick stacks, thus we have access to round trip time measurements and various other metrics around our quick stack. And what was very surprising to me was that our median is currently around 25 milliseconds. I would have expected way higher, around 50 or 75. And I think these kind of numbers, maybe not this in particular, but in general, like grounding yourself in data can inform your next protocol design. And this is definitely a helpful one. One caveat here is we landed this metric only recently. So this is only for our Firefox nightly population, which is around 15,000 users. This will hit release soon, and then we'll have the roughly 200 million monthly active users on the metric as well. I mentioned we run our own quick stack, thus we handle UDP. Thus, we're also in the business of deciding what MTU to run on the internet. But we also see, as we're mostly downloading as a client, what the servers use. Now, most of them used 1217. That's, I believe, 1080 on the IP layer with IP headers. But we also see some brave souls running 1448 and sometimes more. If you're curious about that, the metric is again linked below. With that.
Yeah, and so now we'll move on a bit to our send path. So yeah, we're a browser. So obviously we're sending a bunch of GET requests, but we also do actually send data. So about 6.5% of our connections actually ever grow their congestion window, so they ever send enough to not be application limited. And then of those 6.5%, only 5 to 6% send enough to exit slow start. We also only see congestion events in the 95th percentile and up. And then in the 99.9th percentile, we see 6 congestion events for one connection. So really most of our connections never really enter steady state of congestion control. And then to move on, we also implement ECN. And so we can see, we set EC to 0. And so we can see how many paths support ECN. For us, we see about 60% of ECN capable paths, and then about 40% where the ECT0 bit that we set is actually stripped. We only see 2% of black holes, so that's good. Ideally, it would be 0. But yeah, and one thing that's really interesting is that for us on our send path, we do actually see 15% of our congestion responses are coming from CE marks. So yeah, somebody's out there and marking CE. So yeah, in general, of course, it's good that those CE marks exist because it's nice to have a congestion event without a packet loss. And we also implement alternative backoff, so we react less to ECNCE than we would to loss. And then I have something that's very new. So we implemented this during the hackathon, and it's a new telemetry probe because we can also observe the receive path of ECN. And so we can kind of see how many servers support ECN. And so this is very fresh data, like first day data from Nightly. And yeah, we see that about 4% of connections that we receive have marked ECT0, and of those about 0.75% then actually have observed an ECN CE mark. And then the same thing again for ECT1. So this is quite nice because this metric can be used to kind of observe the rollout of L4S eventually on the networks. And then, yeah, we're almost out of time. So you can query a lot of this yourself. There's some different links here, mainly GLAM, which is our public dashboard, and then some curated dashboards and stuff like that. And so, yeah, for the higher resolution data, if you do bring a research question and add an interesting browser vantage point, then feel free to contact us, and we're happy to help you find the right probe. And yeah, thanks.
Thanks a lot. What is this mic doing? It's really nice to see all this data and have them available. I have a very quick clarifying question on the previous slide, because you said out of those nearly 4%, it's 0.76 at CEE, or is it?
Yeah, sorry, then I
total?
misspoke.
Okay.
So it's 0.76% seeing ECT0 and ECNCE. So about like 15-20% of those that set ECT0 see CE. So maybe this motivates some server implementers to implement ECN.
You had a slide, hi, Robert Ripe, NCC. You had a slide about V6, 20%. Is that number of proportion of connections or proportion of bytes?
This is requests. We do have connections. I don't know whether we have bytes. I can provide that if you want.
I would be interested if the difference is major or not.
I don't know, but I think we have per connection, yeah. Also, something I forgot to mention here. This is global. Kersham asked me to raise this here. This is the global number. We can drill this down by country. And so that might be something interesting, but that requires more work from our end.
All right, thanks so much, Oscar and Max. Johannes, if you could come up. So awesomely, Johannes will be presenting a piece of work that's already been accepted for IMC in October of this year. And the two reasons that's cool is first, you get to scoop an academic conference, but also you have the opportunity to help them improve the work potentially before it's published. And also, if you're a researcher, think of bringing it here so you can learn what the community reaction to it be before you present it. Johannes, so this is a full paper, so this has 15 minutes. And you can, let's see, did you get? Yeah, you got the clicker already. She's ahead of me. Go ahead.
Cool, perfect, thanks. Yeah, this is joint work with Sebastian and Anja from MPI and Tobias here from Technical University of Vienna. And what we looked at is traceroutes. So I guess most people here use traceroutes at some point in their life. It helps to debug what is happening or see paths on the network. Also, most people, I guess, know that they are not always perfect. Sometimes TTLs are not properly reduced, or there are tunnels that are hidden in traceroutes. The thing is, we didn't expect is that traceroutes, TTLs in IP packets are completely rewritten and jump to a drastically larger value. When we look at this in an example, we have a small network with multiple hops. We want to do a trace route from source to destination. We send a probe with TTL1 as normal. It should be dropped and an error message is returned. Now, second probe, 2 hops, third probe, 3 hops. So far, so good. Now, what happens if node 2 does not reduce the TTL, but rewrites it to 255? Well, the packet travels through the whole network, directly reaches the destination, and if we get a response, we get a response. So what we would infer from that is basically that we have source to destination with 2 hops in between, and it hides a complete AS and parts of a second AS. And the thing here is we actually found this. So this is happening. This is not just a theoretical example. And this impacts research, but I guess also operators that need to debug something and look into networks. So in this work, we looked into this. We checked how prevalent this is, who is involved in this, or which networks, and whether this is new or exists for a longer time. How did we do this? We started with a controlled measurement. We set up a node in Germany where we can capture all the traffic and see incoming packets. And then we used RIPE Atlas to run trace routes to this probe and check what we see at the end. We did this in 2025, November, and we were able to run trace routes from around 11,000 IPv4 capable probes and 5,700 IPv6 capable probes, 1 trace route per probe to our destination. And what we find is, yes, that for 365 of those trace routes, we see a TTL rewrite to a drastically larger number, and those probes are in 63 different ASs. Also, this is not only IPv6 or IPv4, we see this in both protocols. This is not a drastically large number, but it's still a relevant number and can have widespread impact. Now, this could be our vantage point that does this on Ingress or something and not be a problem of the internet. So what we did is we looked at the last visible hop that we saw in the trace route before it reached our target. And we find that this hop is, in a lot of cases, for example, AT&T or Orange. So this happens in tier 1 providers. We find this in smaller networks or in content providers, so Microsoft or Cloudflare, where also RIPE Atlas probes are hosted, and this happens. And when we look at the rewrite location, so where is the probe related to this last hop, we see that it's mostly in the source AS. So it's mostly for those probes that are actually in AT&T or Orange, and you only see whatever happens in those networks, and then you directly reach the target. And in those cases, we are sure that this destination has no direct link to all those networks, and we receive traceroute probes with a TTL of 240 to 250. So there happens a rewrite to 255 in those cases. We not only see this in the source AS, we have a bunch of traceroutes where the last hop doesn't really respond, so we only get an asterisk basically. So we can't map those to targets. And in some cases, this happens on path. So Aurelion, for example, does this also for transit traffic through their network in some cases. This mapping to an AS is obviously not perfect, mapping IP addresses in traceroutes to ASs, but this is the best we can have. And we didn't use any existing methodologies to improve this, like alias detection, because in those cases, we don't really have the relationship between hops anymore, and the existing tools break. Now, this is only a small set. How can we increase this to a larger scale? What we did there is we used all existing RIPE Atlas measurements that are freely available online. For those measurements, we don't have the capture point, so we don't directly see the incoming packets. But whenever the trace route results in an ICMP error message different to a time exceeded one, so port unreachable, destination unreachable, this error message should contain the original packet that was received as a quoted packet. And in that quoted packet, we see the TTL, so the quoted TTL, and can use that value as an indicator what the destination actually saw. So when we do this for 1 day, we see out of around 200 million trace routes they publish on that day, for 2 million, we see an ICMP error message by the destination. And when we look at the results, we have the quoted TTL on the x-axis, and we have the number of traces with a logarithmic scale on the y-axis. For most of these traces, it's correct. So the value is 1, how it should be in a trace route once it reaches the target. However, for 86,000, it is larger than 1. Still, around 75% of those are between 1 and a small number. I assume it took a different path with a different length, or it was not reduced at one hop. So we don't consider those as rewrites. However, for the remaining 25%, so in this case 23,000 of those traces, we see a rewrite, and we see those rewrites to 3 basically different groups of values. We have one around 64 and slightly smaller. We have one around 128 and slightly smaller. And the majority is at 255 and slightly smaller. One caveat here is if you want to use this yourself, RIPE Atlas, the trace route, for example, has a liveness check. So if 5 consecutive hops are unresponsive, the trace route tests if it can at least reach a target, and for that sends a probe with a TTL of 255, but that is indicated in the results and can be filtered. So we see that. One interesting case here is the gray dot at around 128. So those rewrites are not only into a larger direction, so it's not only setting it to a larger value, but in some cases, if the TTL is around 200 something, it also reduces it to 128, or that path was incredibly long, but I don't think that was 127 hops long. With that, we can now do this over time based on the historic RIPE Atlas data. So what we did is we took 1 day per 3 months since 2018, and this is not a new phenomena. So this is happening for a long time already. What you have is on the x-axis, the respective dates. On the right y-axis, you have the black line, the number of traces with a quoted packet where we can extract a TTL. So it's increasing from a few trace routes that have this information to around those 1.8 million that we saw. And then on the left y-axis, you have the percentage, how many traces are impacted, where it starts at around 0.1%, so very small number, to around 1% by now. This increase does not necessarily mean that this is happening more often or in more networks. It could also be that more traces are conducted on a regular basis, and it's just captured more often. So this is basically what we found here. We also saw this in KIDA ARC data. The most prominent node there is an IPv6 or multiple IPv6 probes in AT&T, and all of them are basically blind and can't run trace routes. So the rewrite is happening for all outgoing connections. So this is happening. This impacts research. This also impacts operators. I had a discussion here where this case was seen this week and reported to them. That Aurelion has suddenly a new link to them, which they don't have. So using this might be difficult. It's out there since 2018. We don't know for all cases what it is. We don't know for most cases what it is. We talked to some operators and some vendors that there might be bugs or misconfigurations that, for example, a multi-label MPLS stack might not be properly popped, or not both labels are properly popped, and then the wrong TTL is written to the packet at the end. With that, I'm at the end. If there are any questions, let me know. If you want to discuss this afterwards or have ideas why this happens, we are open for any ideas. Thanks.
Lars Eckert, Mozilla, love a mystery story. So thanks for sharing this. This is probably wrong, but I'm going to say it anyway. Are these just bit flips? I mean, the checksum would be invalidated, but the patterning of your clusters makes me wonder.
I don't think they are bit flips, because then, I mean, we saw this also outside of trace route. So it's not always when the trace route would, or the probe would be reduced to 0, and instead of 0, they set it to 255. So I think if it's a bit flip, then too many bits need to be flipped.
I meant random corruption in the TTL.
But also then multiple bits in sequence need to be.
This is why I said it's probably wrong. Thank you.
Go ahead, Robert.
Hi, Robert for Ripe Atlas. We have data going back to 2010-ish, so I would be curious if you actually went further back than 2018. What would you see?
So
Data
I
is
think the
there.
Ripe Atlas, like the online data is not complete historically because of some API changes, if I'm not mistaken.
No, it's there. You can get
Okay.
it. We can talk offline.
Yes,
I can help you with that.
We can definitely.
The other observation is, yes, indeed, the network has been growing ever since day zero. So, some of those numbers go up naturally. But I'm happy you do proportionally as well. And I would encourage you to do more of that because, we do more and more dense measurements.
Yes.
So the same network is also doing more, but it's also growing. So I wonder what the effects of that are.
Yes. Also, Ripe Atlas is not running the same trace routes every day, so that might also impact the data over time. It's not a perfect time series, but yes.
Well, thanks, Johannes. Oh, we got somebody else. Benjamin, you can go.
Hi, Ben Schwartz, Meta. So as I understand it, TTL was originally introduced as a defense against routing loops, against eternal packets when you have a routing loop. And what you're showing here is that actually there are a lot of paths on the internet where the TTL doesn't decrease. So I wonder, do you think that there are paths out there that have eternal loops as a result of this? And if not, do you think that the original purpose of TTL is moot, that it turns out even without TTL, we're doing fine?
Yes, so I don't know if there is a case where it loops infinitely, because then the rewrite has to happen somewhere in the loop. I mean, it might happen. We've definitely seen some cases where the traceroute ended in a loop, and it looped at least for, I don't know, 200 something hops. So even there, the packet will stay longer in that loop. I still think TTLs are valuable and should be further used. And I guess most operating systems don't use 255 as a default anymore. So all of those packets have an impact on the network, not only on trace routes, but in general, increasing that to a drastically larger value is a problem. I don't think it's on purpose, or I don't hope it's on purpose for some networks. In most cases, I guess it's a bug or misconfiguration. Yeah.
Thank you.
All right, thanks a lot. Next up, we'll have Nalini Elkins talking to us about some measurements about post-quantum TLS. Nalini, you got 10 minutes.
Okay, I'll talk fast. Everybody, you might be walking around, everybody's talking about post-quantum, this, that, and the other thing. There's a lot of algorithms that are being developed, a lot of arguments are being had. One of the arguments is about the signing keys, how they're going to grow. The stuff in the red is kind of what we're doing today. And you can see that both the bytes in the signature and the public key are going to grow. And so they're coming up with something called Merkle tree certs, where, you have a tree hash and you're not necessarily saying, sending everything, over it and how you're going to, keep track of stuff. So the question is, how are we supposed to deal with that in terms of deployment? Because enterprises use certificates for a lot of different things. And so I did some deployments of what are enterprises doing today. And I did the financials horizontally, that is large banks in US, India, and Latin America, and healthcare vertically. That is, we have private health insurance in the United States and the hospitals and healthcare. So if we just look at post-quantum hybrid adoption, so you'll see, I hear a lot of people say that we've got 69% post-quantum for ML Chem. And so why is anybody even talking about it? And that's only true of the large internet companies. You can see that some of the other regions, let me see if I can focus in on some of this, is like some people are approaching, what is that one? That, you know, maybe Latin America or the hospitals are doing real well. But one of the, and this is measuring public websites, but what other people tell me is, you know what, this doesn't even matter. I mean, there's people that are using TLS 1.2 and 1.1 today, and who cares if the website is hacked anyway? Banks need to convert their backends. Who cares if the website is hacked? Well, I don't know so much. So one of the other things I did is I looked at the certificate composition with MLDSA 44, which is the biggest key size. And you can see it's going to start taking up quite a bit of the cert now. But you can see that the average handshake time which is now what we have. Right now, what we've got is that the cert time to process the certificate is maybe about 25% of the total handshake. And that's going to grow to about 50%, which sounds real bad, but still for a lot of handshakes, that's only like maybe 150, 200 milliseconds. So the question is like, you know, is there really a problem with this whole stuff? And does everybody have to do Merkle tree certs? I also measured the cert chain composition, you know, who's sending big cert chains, and maybe even if we just got rid of one of the intermediate certs, that might buy us back that 180 milliseconds that we were concerned about. So, you know, so how are we going to do this at enterprises? Our browsers, they're probably going to do MTC. How do we need to handle that? Our enterprise is going to do plain certs. Yeah, so this is interesting, and we had an interesting discussion in plants about it. And we're thinking about putting up some of our own test websites so enterprises can test some more, get some more learning, and start to do more things. That's it. I went fast.
Yeah, perfect. You saved us some time. Thank you. We do have time for questions if anybody. But I guess this is also, you just started the work, so this is ongoing work.
Sure. Yeah. No, I mean, we're going to keep doing it if there's, and certainly we can bring it back if there's interest. You know, as I say, I've gotten mixed reviews. Some people think this is real interesting. And other people say, well, you know, I mean, these banks are doing TLS 1.2 or 1.1, some of them anyway. And so, like, you know, I mean, people get what they get, right, for doing that, which you can't say no, but there you are.
So thank you.
All right, next up we have Robert Richter bringing us Understanding DNS Dynamics over the Starlink Network. And this is another 10-minute presentation. And overall, we got about 10 minutes to spare, so there'll be some time for questions and comments after this. Let me get.
All right. Hello, everybody. Thank you. So first of all, thank you very much for the opportunity to be here. We're going to do a little twist now in terms of what networks we're looking at, and we're looking at Starlink DNS here essentially now. This is work that has been published at the IFAB networking conference a couple months ago, so this is quite new. And first, let me elaborate a bit on why we actually do Starlink studies, even though most of you probably already have heard enough Starlink talks also during this IETF. But first, a little story that I had while flying here is actually that in the plane I boarded, there was free Starlink Wi-Fi accessible for everybody, and it was quite decent actually. So hot RFC talks were quite watchable during this time in the plane. Maybe that's the future, I don't know. But I know that Starlink has rolled out a big mega constellation by now of over 10,000 satellites. So yeah, it's quite worth studying by now. And actually, what I did a couple of months ago, or quite a while ago now, is also just have an exploratory measurement in RIPE Atlas actually over Starlink, because RIPE Atlas, if you don't know, has more than 100 probes by now deployed operating over Starlink. So you can do quite some measurements there if you want to do some studies on Starlink. And what I learned there is basically, Starlink DNS is decent, but it's still bit of differences by country, and I just wanted to learn more about it, and that's what I'm going to bring to you here, what I learned during this time. And so what did I actually want to find out during this study? So first of all, I wanted to find a bit of what actually Starlink does in terms of DNS, especially what does Starlink default to, and what are you as a user going to use when you use Starlink. And then, of course, I want to learn how does Starlink actually, or Starlink users observe latency if you try to do some queries there, and where does this latency actually come from? So yeah, and in the end, I will give you a little overview what we can here as IETF community learn from that. So let me first give you a bit of an overview how resolvers, users of Starlink see resolvers in Starlink. So basically, if you didn't know, you can use Starlink even if you don't pay for it. So there's still internet connectivity in there for exactly 2 sites, and that's starlink.com and spacex.com. Probably you can see the use case here already, which is just, you can resubscribe and pay for Starlink. So that's a whole use case there. And you can get basically this connectivity over this little resolver there, this 34.145.127.1. So this is nothing that I came up with. It's just documented by Starlink. It's not really a strong resolver. It's just something there for those unsubscribed users. But also the more interesting thing here is basically how do actually resolvers set by default for users that actually pay for Starlink, which probably are most of them. And here you have basically a choice between setting yourself a resolver, just a public one like Cloudflare or something, or use the SpaceX provided infrastructure for Starlink. So yeah. So now let's look at what we actually can see for Starlink users in terms of latency. So how fast will it be for you? And for that, as I already said, we use the RIPE Atlas infrastructure. So there's quite a bit of vantage points possible. But of course, RIPE Atlas, as most of you probably also know, doesn't offer every single DNS protocol that we maybe want to study. For instance, here, all sorts of DOE protocols. And those measurements we basically do with our own Starlink antenna deployed at our university. But of course, it's still only a single vantage point. And what we see there is, first we look at the historic measurements from 2025. And the good news is, if you're a European and use DNS, it will be great. So very good performance here, especially the upper parts of it. I hope this works, yes, here. These are basically all European countries, and latencies are very, very low. Probably, but if you're not in Europe, your latencies are way down, even for DNS over UDP, which is the most basic protocol probably here. Maybe I want to draw your attention to the lower parts here, like North America even, but also South America and Micronesia. So those places where we don't have really lots of terrestrial internet infrastructure. So yeah, but let's look further into this. So we want also now to catch a bit of performance in Starlink over the different DOE protocols. So the really new stuff. And the nice thing is, so this is all recorded from our own dish, which is connected to the Frankfurt POP. And the nice thing is they work quite well. So this is to be expected, actually. Each of the DOE protocols works quite along the number of round trips they actually require, with DNS over UDP being the baseline here, with about 20 to 30 milliseconds of latency. Yeah, let's advance further here to the interesting stuff. So let's talk about what actually causes all of this DNS latency in Starlink. And here we use a little methodology that is by now used by a couple of researchers. So we use the property that Starlink employs a CGNet. And what that means is that you can run trace routes essentially and see this 100.64. something. And we assume, and others probably as well, that this is the first terrestrial hop. So the Starlink constellation in itself is sub-IP layer, so you can't really observe it using trace routes. But looking at the latency that you get from those trace routes to the CGNet hop, as I call it, likely this is the first thing on the terrestrial segment that we can observe. And we use it basically to dissect the difference between how far, or in terms of latency, how far is the first hop distant to the user antenna compared to the whole latency. And what we see here again for the European probes from Starlink, here on the left side, it works well. So again, Europeans are privileged here. But if you're in Philippines, Jordan, Colombia, and stuff like that, you will still have a big overhead from the terrestrial part. So where do I want to go from that? Actually, is actually already what we should work on in the IETF. And that is that this whole thing is similarly also observed for CDNs, and this is a routing problem likely. So we are uncertain how well chosen the POPs here are, and in many cases, these POPs are ill-chosen. So we have a large routing problem here that produces a big overhead also for those props in more distant countries or more distant positions. So yeah, I want to motivate here a lot of the work around the satellite routing, and we also already observed quite a bit around this. So we had a side meeting on LEO satellite routing. I'd also in IP WASM, and I think there was also a talk in Space Working Group. And with that, I'm open to the discussion, and thank you very much.
All right, we got a couple people in the queue. Lorenzo, you're up.
Lorenzo Colletti, is there a reason you didn't, I don't see any IPv6 measurements here, but I looked at the Starlink, the IP addresses provided by Starlink link that you have on one of the slides, and they do provide it. You just didn't bother to measure it, or?
So we didn't measure it in this case. Likely, I wouldn't assume there's a big difference here observable. Of course, our traceroute measurements wouldn't work this way anymore, so we couldn't do this anymore because we don't have the CGNet. But that would be future work, essentially. Yeah.
Well, presumably the CGNet is where the V6 traffic egress is as well. But it sounds like you just could have measured it, but you didn't do it. Okay, thank you.
And Ben Schwartz, you can go.
Hi. So am I understanding correctly that the conclusion is that essentially SpaceX appears to be operating DNS resolvers at a subset of the peering locations?
So, sorry, can you repeat your question? I didn't quite get it.
So my question, okay, if there were a DNS resolver co-located with every SpaceX terrestrial peering location, then we would expect to see, I guess, what you see in Germany, where the latency to the DNS resolver equals the latency to the first terrestrial hop. So do we conclude that resolvers are just present at a subset of those locations?
So first of all, the SpaceX resolvers itself, they are not public, so we didn't actually target them explicitly to get it out of the way. That's something that we would still have to find a methodology for. It's probably possible by doing it over the RIPE Atlas probes that haven't defined a specific resolver. But yes, of course, We also don't know if they are co-located actually with the POPs. Probably they are. And yes, then we would probably also see what we saw for the German probes. But that's also something that we in the end found that would be quite interesting, also in regards to the capabilities of those SpaceX operated resolvers.
You said you didn't target them explicitly. I guess now I'm confused. I thought from that you were measuring latency to the SpaceX provided DNS resolvers.
No, not explicitly, no. We mostly use those resolvers publicly accessible.
Okay, so you were, then let me reinterpret this. It sounds like you are saying that Quad 9 or other public DNS resolvers appear to be approximately co-located with the SpaceX peering points at a subset of the peering points, including in Germany. And so in the German example, essentially Quad 9 or other public DNS is essentially at the same location in the network as the peering point, but in other places it's farther away.
Yes, essentially.
Okay, thanks. That's very helpful. Yeah, for what it's worth, I work in DNS, and I would be interested to learn more about the behavior and network topology of the SpaceX operated DNS resolvers.
Yeah, Lorenzo, I just wanted to follow up. I think that's what Ben is asking. We basically what we're seeing here is anycasting, right? If the anycast resolvers are close to the Starlink POPs, then the number is low. Otherwise, it's high, and that's kind of you're just figuring out how closely the Starlink network interconnects with Google, Cloudflare, and Quad 9. Yeah.
Yes, to some degree, even though Anycast also showed some deficiencies, like in earlier work on CDNs. But I don't want to put myself too much out there because I don't have everything in my head for that.
All right, thanks a lot, Robert. Up next, we have another published paper. Newton, you can come up. This is a paper from PAM 2026, published in March of this year, on the future of DNS privacy. Another 10-minute presentation.
Good evening. I'm going to present this paper, The Future of DNS Privacy.
Newton, could you point the mic up a little closer to you or be a little closer to it?
Is that better?
Thank you.
Okay, I think I'll take it out. Okay, so I'll be basically presenting a paper where our research group was looking at the impact of encrypted DNS on user experience as the core outcome. So I basically was the presenter for the paper, but not one of the co-authors. So the question is, why do we want to study this? Because when we look at the interaction between what DNS lookups result into versus what the user gets out of it, there is the high likelihood that there may be an experience felt when they are browsing. So we all know that with a UDP, without encryption, we expect it to be fast. But what happens when you introduce the encryption? So basically, we're looking at DOQ and DOH3. And the main thing we want to find out is, do users actually experience performance differences due to any encrypted DNS enhancements? So the research looked at three core questions, or was trying to answer three core questions. How ready exactly is DOQ and DOH3 deployments for production use? And in specific, because we're looking at DOQ and DOH3, we're actually looking at how they implement QUIC in the protocol. Then the second thing, we wanted to see how the web performs when you have, or the web performance when you have encrypted DNS, and also we also wanted to look at the impact of complexity when you have on web complexity when you have encryption. And so basically what we are trying to answer is what is the performance penalty of encrypted DNS on user experience. So the measurement campaign proceeded in 4 phases. So we did the setup where we had basically the initial scans were done using ZMaps for IPv4 and a hit list for IPv6. The second phase, we had the resolving of the measurements. So we looked at the RTT, zero resumption and zero RTT, both for DOH3 and DOQ. Then we looked at the website performance. So basically here we move from large scale measurement to actually real user experience, simulated, so to speak. Then we have website complexity analysis. So these are the measurement values. We had 3,000 plus DOE resolvers, 75,000 DNS queries, about 1.9 million page loads, and about 570,000 websites which were accessed. So our first major finding has to do with DOQ deployments, and we noticed that they are in essence more mature, if I may use the word, than expected. So when we look at the values we got in terms of DOQ and DOH3, we actually see that from the data that we collected, DOQ performs far much better than DOH3. So in terms of session resumption, we got 94% actually show that they actually have session resumption, 65% on the other hand for DOH3. And our DOH3 measurements did not show support for, we did not observe zero RTT support. And DOQ median latency was much, much lower than DOH3. So in essence, one of the things we noted with DOH3 was that we had about 391 failures, which was about 70% of the data which we collected. Then we also noted that from the DOH3 data set, or portion of the data set, there was about 85% which was attributed specifically to AdGuard resolvers. And this had a major impact on the results of the DOH3 values. Our second finding was that resolver deployment matters more than protocol choice. And this I will explain further. When we look at the results that we have, it's very clear that number one, I need to mention this, that we actually looked at how the resolvers work in separate, and we also had a small subset of resolvers, which is what we call the all resolvers, where all 3 protocols, UDP, DOH3, and DOQ were implemented. And what we noted is that when we look at that small subset, they outperformed all the others when they were looked at separately in general. So one of the observations we make was that DOQ in general was had much lower average RTTs than DOH3, but of course not as low as UDP. Then we also noted that, and this is very important, that multi-protocol resolver deployments actually outperform single protocol deployments. And then the third thing we noted was that the AdGuard resolver outliers resulted in a long DOH3 long tail. So we also noted that 95% of the DO53, the UDP resolvers that were in the intersect subnet, so the subset that was had all the protocols, responded in less than 30 milliseconds, which was really good. We also noted that the subset DOQ outperforms average DO53. And this is very clear when you look at the graph. It shows that Quick, which is under the intersect resolvers, actually performs much better than UDP. It's actually quite clear from the graph. And then the question then is why? It's simply because the multi-protocol resolvers were outperforming the single protocol deployments. Then the third finding we found was that encrypted DNS has a negligible impact on user experience. And this does not mean that page load time is negated, but what we actually look, not page load, but DNS querying time. But what we're actually looking at is what's the difference when once the DNS query is complete, does it affect page load time? And we can actually see there's barely any difference. So whether it's UDP or DOQ or DOH3, it didn't matter. The difference was very minimal. And the time difference in essence was less than plus or minus 1%, so 2 to 16 milliseconds. And in essence, we actually can say longer DNS lookups does not necessarily result in slower web pages. Then the question would be why? And the simple answer is because browsers actually perform, there's some browser parallelism which actually hides that DNS latency. So as the DNS lookup is going on, various aspects of the page are being loaded. Then the final finding was that website complexity does not actually amplify the DNS overhead. So for this, in terms of website complexity, from our data set, we had about 572,000 websites which we looked at. Each had about, on average, a median of 1.2 megabytes, loading about 42 median objects, contacting about 7 DNS servers, with 5 of them at a median being external with a median page load time of 0.9 seconds. And what we noted is that of that time, only about 25 to 93 milliseconds were actually attributed to the DNS query. So this is really small, and the user will not even notice that. And we also noted that in terms of complexity to performance correlation, there's about a 0.45 correlation or less. And we would actually say statistically that there's a weak to a moderate correlation, but it has a very little impact to the user, as we can see from the actual values. And also similarly for the MIME type correlation was about negative 0.2 to 0.3. So similarly, we can say that there was a very weak correlation. So in essence, we say that website complexity increases overall page load time, but it does not have a relative cost effect. It does not necessarily mean that the encrypted DNS impacts the page load time. So what takeaways do we get? Number one, we say that deployment in terms of comparison, DOQ would actually perform or does actually perform better than DOH3. We also see that the protocol, in terms of performance, multi-protocol performs better than single protocol deployments. And lastly, user experience basically is negligible impact because of the encrypted DNS. I do have one more slide, but because time is over.
Yeah, we got a little time.
So where do we move from here? So from that work, we are actually currently looking at DDR deployments. We're looking at various aspects, but one of the very interesting things when we're looking at the DDR deployments is that the very same results we saw that DOQ is actually better, but DOH3 is being deployed more is actually there. We can actually see from the data set that we currently have collected that DOQ is barely being implemented by major providers, while DOH3 is implemented, DOH2 is implemented, DOT is implemented, and this is the same across IPv4 and IPv6. So this is being prepared for a different paper. Currently, we are working on it. So this is what I would say is currently ongoing works. I think that should be it.
All right, Lars, you're up.
Lars Eckert, Mozilla. One of the things I do is I help run the TRR program, which is when Firefox uses the DOS server. And I think what you've done here is nice, right? You have a nice setup to measure these servers. I think the flaw is that you scan the internet to find them. And so you're finding a lot of small servers on questionable links, and then you probe them. And those are not the servers that the vast majority of clients are actually going to choose. So for example, like we see DOE resolution times of 10 to 15 to 20 milliseconds, and anything above that I would consider broken. and yours like was 80, and you had a P95 of almost a second, right? So and as you see on this slide, like there's actually no DOQ deployment by any of the large providers, right? And so I think the statement that DOQ is mature and faster than DOE is very questionable. It'll be interesting to see what you find, because I think the methodology you use is fine. I think you're just applying it to the wrong set of servers. We have a bunch of measurements from Firefox telemetry. There was a talk earlier. There's DOE measurements in there that we can talk about. So I think the methodology is great, but the set of servers you're applying it to is questionable, and therefore your results I would be careful with. Thank you.
Okay, thank you. I'll take that.
Yeah, Lorenzo Colidi, I would second that. If you just ask them random servers that you find on the internet, you won't get, performance that is comparable to what an actual deployment is. So I think it looks like you built some really cool tooling for measurement here, and I would love to see the results of this tooling applied to actual DNS servers that you can find that are intended for use. Because these DOQ servers, I don't know what they are, but I don't think they're, expected to be used by users. So if you point these at, for example, if you point your tooling at various ISP servers, or maybe the well-known ones that you have here on the slides, I think that would be very interesting. For example, in Android, we decided not to implement DOH2 at all because we think it's going to be slower than DOU, right? Because it has, connection establishment overhead, and that would be really good to see. So if you could take your tooling and look at the popular DNS servers, which are deployed close to users and so on, they're intended to be used and they intended to be high performance. It would be still very good to see, because on those you'll see, and ideally you could compare within each resolver, you could compare how the different protocols go. That would be very interesting to see. Whereas I think, like I said, the data, like Lars said, the data set that you have is kind of flawed because of these servers are probably, you don't know what they are. Anyway, I look forward to, if you do that, it would be very interesting to see.
Thank you. Thank you for the comment.
Eric Nygren, clarification question. So when you're finding these, are you confirming that they are recursive resolvers, not authoritative servers? Because at least some of the people planning to deploy DOQ are deploying them as authoritative servers, which is a very different footprint and use case than the recursive servers that are doing DOH3. So I would expect them to be set up fairly differently, but would not mirror the behavior you'd expect for like a user resolver.
I'm very sorry. I barely got what you said. Could you
checking if these are user-facing resolvers? Resolvers you find are these first resolvers that actually are used by users? Are they checking that somehow?
I'm not sure really. I'm not sure. Okay, I don't know if I'd say yes or no. What I suppose was that from the data set, what was collected was what was then analyzed. So some could be fast resolvers, some could not be. It's highly likely.
Specifically authoritative servers versus recursive servers.
Actually, one of the things in the paper they were trying to do was look at the connection between authoritative and recursive. So there was a portion where it was considered, but eventually in the analysis, they looked more at DOQ, DOH3 as opposed to looking at the authoritative versus the recursive.
Oh, I mean specifically because many of the DOQ things you're going to find are authoritative servers implementing DOQ. Because I think the use case for DOQ, or the primary use case for DOQ, is not for recursive servers, it's for authoritative servers to implement DOQ. So that might be a big part of the skew you're saying.
All right, thanks, Eric, and thanks, Nelson. So you've got some good hints about characterizing the resolvers for that next paper. Thanks for bringing this. Sorry, I had to kick Tim and Jason out of the queue. We promised 15 minutes each of the next two speakers, and we've got about that much time left. So next up, we got Shyam. If you could come up, his work is detecting and characterizing exposed BGP routers. Both these are published papers. I'll share the link in the chat comments. I can. I'll put the timer up.
All right. Hello, everyone.
I'm Sam, soon to finish PhD at University of Twente. Today I'm going to talk about our work on exposed BGP routers. In this work, we asked a simple questions. How many routers that run BGP, which stands for Border Gateway Protocol, on the internet are exposed publicly to the internet? We may all know that BGP runs on TCP port number 179. So realizing the importance and criticality of BGP, RFC 7454 recommends to restrict that port to its configured peers only. Slow. However, there are many routers in the internet which accepts TCP connection from any host on the internet. They accept BGP open messages from them. Further note, BGP open is the first message that a router sends after TCP connection is established. Then those routers respond back to those hosts with their open messages, followed by notification message or just notification messages. If it is an open message, it reveals or it contains many useful information, such as AS numbers configured in that router, VGP ID, which is also called as router ID, configured in that router. If it is not, then in the case of notification message, it simply tells the initiators to terminate the connections by sending notification message. In our study, we define such routers as exposed routers. Now, to detect such routers, we developed a tool and named it as Scan 179. So the first step of such detection is finding the potential routers on the internet. Since there is no complete and authoritative list of BGP routers on the internet, we used ZMAP and scanned port 179 in the internet. That gives us the potential routers that are running BGP. Then the next step is we created a custom BGP speaker that contains AS number of our institute, BGP ID, and many other necessary things that are compliant with BGP's RFC 4271. Then we send that custom BGP open message to all those 179 responders. Then we collect the responses from them, analyze them, and find the corresponding routers, AS numbers, and many other interesting features, which I'll discuss later. And it was one such internet-wide IPv4 measurement. Let me present our finding in a high level. So we found around 6.25 million IP addresses that responded with GMAP scan for port 179. And we found three main categories. If you see in the leftmost side, 5% of them were BGP responders, which means they responded with BGP compliant message. And the BGP compliant message means either they sent with their open message, either they sent their open messages or they just sent notification messages. We found a higher number of open responders compared to notification only responders. And there are other two categories. The second category is non-BGP responders, which is 86%. Non-BGP means they allow the TCP connections to our probe, but when we send BGP open messages, they either send TCP reset or they did not send anything at all. And you see the third category, which we say pre-TCP responders. It means they did not allow TCP connection to our probes. So ideally, the last two categories are the required responses from BGP routers as per RFC 7454. Then the next step is we identified who are the ASs deploying or managing such routers. If you remember, we had two types of BGP responders, open and notification. In the case of open responders, it's relatively straightforward. We check whether those messages contains public AS number. If it is public, then that is the one managing the router. If not, then we use IP info data to map the interface IP to the ASN. In the case of notification responders, we again relied on IP info. It is because notification doesn't contain information like AS number or many other details as of open message. That's why in the case of notification, we say it's inferred ASN because we cannot confirm it. Then the next step is grouping those responders IP to routers, because generally a router has multiple IP addresses configured on it. So the key idea is to look at BGP ID configured in those open messages and the AS number, because as per RFC 6286, BGP ID is unique per router in an AS number. So we used the combination of BGP ID plus AS number configured in open messages to group those responder IPs to a router. And in the case of non-public open ASN, it means the open message contains AS number other than public, such as private or reserved, because some ASs use internal ASs for their internal configuration, also known as AS configurations. So it means non-public ASN could be used by multiple ASs on the internet. That's why we use the combination of BGP ID, open ASN, and interface ASN to group IPs to a router. Then the next step is we classified routers as internal and border. For example, in the case of internal router, we check the AS number, whether it's non-public. Since those non-public ASNs cannot participate in the global internet, so we can say that they are internal routers. And we define our router as a border router if it is having an eBGP pairing with another router, means having BGP pairing with router in another ASN. For that, the first condition is that the AS number configured in its open message should be public, and the second condition is that at least one of its interface IP has to belong to another AS number. This is based on a heuristic that in a point-to-point connection between two routers, these two routers share this subnet that comes from one of those two participating ASNs. However, there was another category where they have a public open ASN, but all of its interface IPs mapped to the same ASN. In that case, we couldn't distinguish its role as border or internal. It could be either iBGP pairing router or it could be the host AS providing the IP to its peer. So we made it as unclassified category. Here in this figure, you see the summary of our results. We found around 141,000 exposed IP addresses, which correspond to around 20,400 unique routers. And most of them are internal routers, which is 16,000. And there are around 1,127 border routers. And all these routers are managed by around 4,200 ASs. Then the next step is we measured how critical those routers are. So we measure criticality by distinguishing again two types, border and internal. In the case of border router, we use the connected ASs as the metric for criticality, because instability of that border router will affect the connected ASs. As you see in the figure, around 75% of border routers were connected to only one AS. There was a border router which connects to 21 ASs. So you can imagine the criticality of that router. And for internal routers, we use number of IPs configured as a heuristic to measure criticality. It is because number of IPs means number of subnets. So higher the number of interface IPs, higher the subnets. And the instability of that router affects that many subnets of the router. And you see that 60% have one IP and 90% have fewer than 10 IPs. And we found that 10% of internal routers with maximum up to 1,208 IP addresses. There are many other interesting results which you can read in our paper. So to summarize our work, we found a non-trivial number of exposed BGP routers that violate RFC 7454. And there may be multiple reasons for such exposure. We also investigate into those routers. For example, we talked to one operator who thinks that having extra protection for TCP 179 is not necessary because as per RFC 47.1, sending notification only message is sufficient. And other operators, they think that there was really a problem, and when we informed them, they were happy to fix their routers. And the other reason could be the routing stack of BGP routers, where the peer check happens after the TCP connection is established. So I expect more reasons from the audience in this group, and you can read more in the paper. And as a final note, since I am a final year PhD and I am in the job market, so you can check my personal website if you are looking someone like me. Thank you very much for listening to my presentation.
Thanks, Shyam. Any comments or questions? All right. We've got one more paper coming up.
No question answer?
No, there's no question.
Okay, thanks.
Yeah. Please reach out to him.
And Brima, you can come up.
You want to hold it? Or should
I think I can put it here. Let me try this.
I think it's better to push it like this.
Yes.
So this is another published paper and another 15-minute segment of the meeting about route views data. I happen to be working with the Open Science Data Federation. This data is also not just available through route views now, but it's also available through Open Science Data Federation. And your topic is particularly timely because it's about kind of how much chaff is there in the BGP data that's there. So go ahead, you got 15 minutes.
Good evening. I am Ibrahim. I'm also a final year PhD student at the University of Twente. So this work was a joint effort with folks from CADA, Casey Claffey, Thomas Crank of IIJ, and my supervisors from the University of Twente. So generally, like we have a subset of ASs, like the previous presenter mentioned. The internet consists of different ASs, and then a subset of these ASs called route collector peers dump their information to collectors. And this data is really essential for both operational and research purpose. For instance, operators use this data for monitoring their traffic and also for troubleshooting or traffic engineering. And researchers like myself use the data to have a better understanding of the internet ecosystem, for instance, like security research, operation management, and the likes. So typically, routers should only trigger updates if there are configuration changes. For instance, newly announced prefix, withdrawn prefix, or a route failure. So looking at this simple topology, we have ASX and Y, and they each announce a prefix to AXZ, which is a collector pair. So in ASZ's RIP, we have these two prefixes, and also from the origin ASs. So at the end of 5 minutes, if the route collectors collect this data, we expect to see a single copy of these routes in those route collectors. So I don't know, unfortunately or interestingly, like buggy routers or misconfigured routers could lead to not a single copy, but many copy. For instance, taking the same topology again, let's assume router 6 of ASZ got noisy, and for some reason, it just continuously sent whatever it is in its RIP. So at the end of 10 minutes, instead of having a single copy of that route, we have 51 copy of exactly the same information. And this is a problem, of course, for both operation and also for researchers, because we are having a single copy of the same information that doesn't tell us any new information about the route. So our motivation last year, around February 2025, an email surfaced in Nanook mailing list complaining of few prefixes that were unnecessarily like generating a lot of updates or announcements. And also RIPE NCC, who also like run a collector project, which is the RIPE. One of their operators wrote a blog, a RIPE Labs blog, where they kind of emphasize the importance of RIPE, but also talk about the pressure that they have in terms of storing this data. Aside from that, if you look at there were some folks who did some research in Strasbourg, and they sent a survey to researchers to ask them if they have challenges processing this data. And you can see a large amount of respondents actually acknowledge that they have the challenge of processing this data. So our main objective was to kind of look at the makeup of this route collector data, specifically for route views. So to put something into context, noise can be a bit controversial, but in our study, what we mean noise is that if we receive an announcement from a prefix within the space of, let's say, 1 minute without any change attribute, we consider that noise because it's not just giving us any new information about that route. And this, of course, have a problem. Like I said earlier, it increases router processing load and also unnecessarily inflate these MRT files that are used by researchers. So to kind of look at this, what we did was look at more than like a decade of data from route views, which consists of like 2.6 trillion of updates, both announcement and withdrawals. Considering that we cannot also dig deeper into over a decade of BGP data due to processing reasons, we use 2 months of recent data, which constitute of like 83.717 billion updates. So our first goal was to because route views run different kind of collectors, our first objective or like goal was to measure the distribution of like updates across all these collectors that are run by route views. To do that, to summarize our methodology, what we did was like, we count the daily update counts for each collector, and then we aggregate this into 6 months, like let's say bin or interval, and we compute the average and rank these collectors based on this average, then decide which are the collectors that are really contributing a lot of data, and then we aggregate the rest. So looking at the results here, on the y-axis, we have the update count per collector, and then on the x-axis, we have the dates from 2012 to recently. So out of the 36 collectors, like the top 5 collectors contributed over half of the data that is collected by route views. And if you put this into context, out of this top 5, only purge and links collector contributed over 30, almost over 30% of the data. And when we look at this, we found out that most of these data were repetitive announcements with very few withdrawals, telling us that this is not due to the changes in those routes, but for some other reasons. And we found out that, like, let's say over 1/3 of these collectors were each contributing like just about 1% of the data of route views across 10 years. So specifically during this time, like the Perth collector happens to be the collector that collects the largest routing event ever in 2021, which is like 3% of the over a decade of data. So the main takeaway here is that update distribution across route view collectors is highly skewed, and somebody might be saying maybe this is due to the peers that those collectors have, but we look at this and then that is not the reason. So now that we know that, of course, out of these 36 collectors, not all of them are equal in terms of the updates that they're collecting, we wanted to look at, is this due to the peers that these collectors are having or some other reasons? So to do that, we construct a daily update time series for each collector peer-peer, and then we rank this in each day because we wanted to know the heavy contributors. So in each day, we put these collector peers into quantiles, like the top 5% to the lower 50%, and then we determine or we quantify the top contributors. So looking at our results again, on the x-axis, we have the total updates per day. And again, on the y-axis, we have the total updates per day. And on the x-axis, we have the dates. So during like over decades, out of 2.6 trillion updates, like we only have the top 5% collector peers, which on average is just about 16 peers per day, contributed over 50% of the data across the whole 10 years. While the lower 50%, which on average is about 160 peers per day, contributed just like 5% of the data. So this tells us that out of the peers that RouteViews is having, we have very few peers that are dumping a lot of data to the collector. So if we drill down into these few collector peers that are unnecessarily noisy, you can see a very interesting patterns, and that is we have noisy peers across the whole 10 years. Sometimes this peer will be noisy and went quiet, and the other one comes to be noisy again. So the key takeaway here is that noise in BGP data, or at least for route views, is both prevalent but very unpredictable, for the simple fact that a collector could be noisy today, and in maybe 1 week time or few days time, it went quiet, another collector will be noisy. So now that we know out of the peers that RouteViews have, not all of them are noisy, we wanted to also dig deeper within these noisy peers or all the peers to see if this is driven by just a few of BGP sessions, prefixes, or AS parts. So to do that, what we did was we compute per minute update share for each BGP session over the 2 months, and we use some statistical methods to quantify concentration and variability. And concentration here help us to kind of quantify the dominant sources, meaning sessions and prefixes and AS parts, and variability help us to kind of determine the fluctuation of updates across the sessions, prefixes, and AS parts. And we apply the same methodology also to prefixes and AS parts. So if we look at the results here, again, on the y-axis, we have the per minute update share per session, and on the x-axis, again, the dates for the 1 month. So we found out that only 19 sessions, which is just 2% of all the sessions we found in BGP data, constitute of like 71.3% of the updates for the month of December 2021, whereas a huge amount of the sessions were just very quiet during this time. So we found the largest routing event that we mentioned earlier happened during this time. We found it lasted for like from almost about 12 hours, and then this leads to a large MRT files. And when we passed these MRT files, we found almost like a complete routing table. which is like 730K unique prefixes. And in each of these files, we were having around 32 million updates. So what we speculate or assume is that there was a router that was continuously sending whatever it is in RIP. So the main takeaway there was that out of all the sessions that we have within those noisy peers, there are just a few sessions that were unnecessarily noisy. So if we apply the same methodology to the prefixes, we just have the top 2% of the prefixes that account for like 74%, like almost 75% of all the updates within this during this bond, whereas the remaining prefixes were mostly quiet. So the key takeaway is that noise in BGP data is both prevalent but very unpredictable. You cannot know which peer will be noisy today or tomorrow, and it's mainly driven by a very few set of peers. Also, we have few sessions, prefixes, and AS parts that contributed large amount of updates, which are mostly redundant because they're not telling us any new information about route to those prefixes. Also, prefixes are not universally noisy. It is often confined to a few collectors. For instance, like oftentimes in the literature, they call prefixes or origin AS is noisy, but in this study, we look at it, we found out that a prefix could be noisy from one vantage point and not noisy from the other vantage point. So we, out of these findings or observations, we conclude that these noisy prefixes are mostly due to faulty or misconfigured routers and not inherently from the origin AS that originate the prefix. And all these redundant updates, it just unnecessarily inflates MRT files without giving us any new information about the routing state of those prefixes. So we found all these interesting things from the data, but it's still difficult to kind of quantify what is the root cause of this behavior, aside from communities and route flapping. So we seek feedback from the operators who can help us to kind of validate if they observe this kind of behavior in BGP and what could be the reason for some of these observations. So you can read our paper for the full details, and thank you.
Yeah, thanks a lot. So for both this and the previous paper, please, if you have any insights, reach out to the authors, get in touch with them. But thank you for presenting. It looks like we don't have any questions. Okay, so that's the end of our scheduled talk, but we have now Tom in the room who, where we showed the one slide about the IPv6 data in Common Crawl. Tom, do you want to come to the mic and say something? We have like a minute left for you if you want to.
3 minutes.
Yeah, actually 3, yeah.
Hello. Yeah, this is something we did last month to measure how actually accessible things are over V6. So we did this at the beginning of the year from one vantage point in California, and we did it on the top 100,000 hosts ranked by harmonic centrality. And we decided to do it again, but on the top 1 million hosts and also from 5 different vantage points in 3 different continents. And the results are basically nearly the same, like exactly the same, which is kind of embarrassing. But anyway, it's helpful, I think. But yeah, there's a report, like a full report on the thing in that QR code in the top right corner. But also, nicely, my colleague Sebastian at Common Crawl is pushing an update to this thing called CC statistics, or CC crawl statistics, which is a thing that we push after every crawl that we do. And we're now going to include plots of metrics comparing the counts of things like HTTP protocol versions, TLS versions, and IP versions. Happy to answer any questions if there are any, but if not, cool, and enjoy.
Thanks, Tom. I have a quick question. One of the things I've been interested in is how much the largest content deliverers play a part in IPv6 content being available with the data you have. If you haven't done it already, maybe you have, I haven't looked in detail. Can you tell, for instance, like at the Cloudflare, Akamai, whoever, if somebody uses those to host their stuff from their origin, how much are those players bringing v6 content to us? Is that something we can find?
Yeah, you can kind of find that. There's like a nice plateau of Cloudflare content in the original report. Actually, if you go to that report, it's the top link that shows you this nice chart of that stuff. But I mean, it kind of, it varies from CDN to CDN. Cloudflare seems to be pretty good at it, as in pushing v6 support. Fastly is also pretty good at it. But yeah, you can see that from the results.
Thanks.
And the data's
you
all
imagine
open.
some of that came from their default policy, right? I think they got earlier into it was on by default.
Yeah, it seems so anyway, unless, you know, by some crazy chance, like millions of people are going, haha, let's turn on v6, like deliberately. That'd be nice, but yeah, don't know how likely it is.
Well, thanks so much for closing our meeting for us.
Yeah, thanks, Dave, and thanks, Maria.
Yeah, thanks to all the presenters and everybody who asked questions and was in the audience. That's the session. Thanks.
That was good.
It worked out really well. Even so I squeezed into my head.
I wish I would have looked.